Okay, so what I'd like to do is I'd like to start with I'd like to just start talking about the disk I/O problem, because a few people have had it, and talking about specific issues and how you do monitoring and metrics helps Theo. Hopefully we'll be able to demo some of the things that he does for disk I/O and the disk I/O latency. That's when I want to go through methodologies where I'm into developing the metrics. So this will feel a little bit ad hoc to start with, because that's how a lot of it's done at the moment, but we do want to move on into methodologies so that we can generate metrics more scientifically. So, disk I/O. So I've got both Linux and a Lumos set up. If you're completely new to a Lumos is a kernel. It is the active fork of OpenSolaris. It's what a number of companies use for products. Theo's company, my company, and it happens to have dtrace. It happens to have a lot of metrics. It's a good system for just doing demonstrations of metrics on. But of course, I can do Linux as well, or FreeBSD, or Mac OS X. In fact, I was just running IOSnoop on Mac OS X with IOSnoop minus capd, and that shows disk I/O per event. You can see what my laptop is actually doing. If it's going to do something. There we go. Oh. LS-save, what's that? I have MD worker. syslog-d is writing to the system log. Then I have ls-save writing to Apple launch services. Okay. I think, was it Alec Muffet who said IOSnoop was the best tool for Mac OS X? It's flattering. So I want to start with just going through disk metrics before we get into more of the science. The first disk metrics that were added to Unix, using Unix as a case study, was with IOSnoop. And IOSnoop was added to AT&T Unix 7th edition. IOSnoop was developed by AT&T, and now it basically exists on all of the platforms, all of the Unixes. I really like IOSnoop. I think IOSnoop is a model for providing this type of metrics, which is a per interval rolled up counters. Of course, there's lots of other metrics we want. This is just showing one type of it. And I'll tell you why I like it. With IOSnoop, and of course I'm just showing you one version. The Linux version doesn't fit on one screen, which really bugs me. It's more than 80 characters. On this version, we have the workload applied. So you can see the reads, writes, kilobytes read, and kilobytes written. Then you have the resulting performance. So the average length of the wait queue, the average number of I/O that are active being serviced, the average service time in milliseconds, percent of time something was waiting, and then our percent busy utilization metric. So workload characterization, the input to the system, the resulting performance, and I've added an IStat minus E, which gives me error counts as well. I do get asked by engineers who are rolling new tools, what metrics should I add? I'm rolling a command line tool that does stat of X or Y. I don't get asked all the time. It's happened a few times. And I've used this as a model. If you just want that high level, say per interval summary, because it is actually very, very, very good. I can answer questions. I can answer problems of load just by looking at the load figures. I can also debug problems of resulting performance. And of course, errors. Errors need to be included for any component that we're monitoring, because errors can result in degraded performance, especially because systems are designed to be highly available. And so even though devices will fail, the system will continue. It's been designed to continue. That's now causing a performance problem, and it can often be overlooked because you're not looking at error counters. You're looking at the latency counters or various other counters. So that's the first command, iostat, the Linux version of it. Very similar, I love it. It's got, it's giving me the CPU averages, but I can also look at the workload applied. It's also showing me what's happening within the Linux IO scheduler, so that I can see what's being grouped. These metrics are interesting. How many read requests were merged per second? If that is high, I can tell that I've got a sequential workload. So it's helping me identify workload types. Similar metrics reads, this is the IOP counters, I've got throughput counters, and then I can look at resulting performance. One thing I don't like about the Linux IO stat is that there is no -E option. So I can't look at errors. I want to see errors per device. Anyone know how you do errors per disk on Linux? Is anyone monitoring disk errors on Linux?
We try not to use disks on Linux.
You try not to use disks on Linux.
You can look at the demessage string buffer and hopefully correlate kernel events, but then you also need to decode that timestamp that doesn't go up monotonically. But yeah, you can do that.
Okay, yeah, because I love demessage. In fact, every single performance issue, if people watch me debug a performance issue, the very first thing I'll do for everything is either run demessage or look at the system logs, depending on the system. Because so here's the Illumos system, tell variety in messages. It's simple to do. Kernel engineers can sometimes be kind and add meaningful stuff in here, and it's not complete because there are missing metrics, but you can immediately diagnose that there's actually a failed condition. Errors are great because errors are objective metrics. If something has errored, it is bad. The end. You go fix it. With latency, like we're looking with IOStat, these latency numbers, what is bad when I'm talking about service time or Linux's IO wait? Oh, sorry, the A wait. What's good or what's bad? That's a subjective metric. It depends on your requirements, your expectations. I can give you some numbers that I like to use myself, but it really depends from environment to environment. So one thing that's useful to learn is the separation from objective metrics, which it is fact whether it is good or bad, and subjective metrics where it is based on various other requirements. As an example of the difference, I have two customers who have different latency requirements. One of them is doing high frequency trading. And so when in the IO path, when they have 10 microseconds added or 30 microseconds added, they get really, really worried. They don't like that. Whereas another customer who's doing mobile phone things, they're on a network where huge latency is common, tree transmits are common, people are on their phone, they go through tunnels, and for them, it's 100 milliseconds is really the worry point. So I have 4 orders of, or more orders of magnitude between these two customers. Subjective metrics are a pain. I really don't like putting traffic lights on subjective metrics for that reason. Because traffic lights where you have the red, green thresholds, there's no general thing that will apply for everyone. Yes?
But the thing is, if it's a change from the current process state, then you do want to flag it as red. If I'm almost always within, let's say, 10 to 30 milliseconds, and all of a sudden I start seeing a run where almost everything is 50, 51, 52, 53, 55 milliseconds, I'm going to look at that to see if my disk has gone bad or something along that line. So that I would flag.
Right, that's anomaly detection. And right, that's an interesting metric because I can look at history. I know that this is outside the bounds. I'm reminded of a visualization where they do this in medicine as well, where they're monitoring a patient with various statistics and they have a visualization so that they can know if the patient has ever exceeded various thresholds, because it's just the change in variations is itself an interesting.
Important. The absolute value of, for instance, blood pressure doesn't matter. The question is going up or down.
Right. So that can be interesting, and you can debate whether that should be red or brown or some other color, because red means bad. Red means stop. So I'm totally fine with using traffic lights on objective metrics, where a disk has failed, it's red. CPU's failed, it's red. You know it's failed. The end. So I was talking about IOStat. Someone mentioned demessage, which is a great way to bring up errors and objective metrics. What other way do I get error counters out of Linux and disks? You can.
Smart control.
Yeah, Smart Control. Smart Control has a whole heap of stuff.
That's right about half the time.
It's right about half the time. Yeah. There is another way. You can actually dig it out of sys somewhere.
So one of the important things is really disk temperature. So when disks go over a certain temperature, they go into the rewrite verify mode, which is about 20% the normal write through throughput. Sorry, 20% the normal write throughput, and half of the normal read throughput. And that's when we were looking at that, so what we call disks go or go slow.
Interesting. So number one cause of disks is disks getting temperature, getting too hot.
Yeah. I mean, it can just be that you might have a CPU fan that's failed on one of the CPUs that happens to be near the drive. So that will do that. Another one is if the fan is slightly, I think the phrase is elliptical, as in it's off the bearings and it's causing vibrations. Disks that detect vibrations also don't start to low speed.
Yes.
Vibrations are bad.
Vibrations are bad, as we've.
But the song clearly says good vibrations. So now you're confusing me.
So how many people have seen the video of me shouting at disks? So a few people. So I had all this email from people saying it was a hoax, and I also had comments on YouTube saying it's a hoax. I also had all these emails from drive manufacturers saying we've known this for years, and one of them sent me a white paper from like a decade prior where they were conducting sound experiments on disks, where the disk was hanging from these rubber bands, it's in this apparatus to separate it from. It's like, yes, like we've been writing papers on this internally, we've known this forever. But the public didn't know it, so it's I've popularized, I didn't discover it because I know that the drive manufacturers knew this very well, but I certainly popularized the dangers of understanding that vibration can be a real issue. I also get emails from, there's been a few startups who now sell it as a service. They sell...
Shouting at drives?
No, they should hire me for that. Like, I'll be the number one employee. It's a service. They will put rubber mats under servers and put rubber grommets here and there. They have all these techniques they've come up with for dampening the sound vibrations in data centers. But it can show up where, as John said, where you've got a fan has now entered a failure mode where it's got an elliptical pattern or doing more vibrations than usual, and that's really messing up with the disk, messing disk performance. So you're monitoring those things to help debug why the disk latency goes up. So I want to start with ISTAT. ISTAT's great. It's got all those standard metrics. Now, yes?
How do you feel about DStat?
Which one?
DStat.
DSTAT's the colored thing. The dim.
I wouldn't put it, let's say it's a Swiss Army tool that takes all the individual ones and puts them all together for you in interesting ways.
I like it not because it's colored. I like it for that reason, and I like it.
Coloring's useless.
Yeah, I like it for that reason, and I like it that it's pluggable. Because you can actually write extra modules for DStat and get it to incorporate other things. And also in many operating systems, the tools we've used like VMstat are really getting long in the tooth. And DStat is the sort of thing we need to be exploring, is coming up with a different starting point when you hit the command line, instead of running VMstat, to do this stuff. So lots of things I like about it.
Now, have you found that it does its correlation repeatedly and properly across all the stuff? That is, when you see something occurring in one set of statistics, the other set of statistics sort of makes sense with it. Because we sometimes see what, basically it's a capture problem, right? You can't really read everything all at once and capture it with the proper granularity.
Yeah, I'd have to look at its implementation for that. Because the kernel counters are generally maintained all the time. And so...
Presenting them in context side by side is what it comes down to. And I think this is what I categorize as the visualization problem. And someone really said, it's not a collection problem, it's a presentation problem. It's like, the counter might be there, but and when you put two counters that are correlated side by side, it's immediately obvious, oh my gosh. But if you don't look at them at the same time on the same screen,
Right.
it doesn't make any sense whatsoever. And sometimes it's just serendipity that you happen to look at two things and you're like, oh, that's high and that's high. Clearly there's something going on there, and it basically, the two together create a giant flaming arrow pointing right at where your problem is. But if you hadn't happened to have noticed that,
It's also a
For some
really,
cases, they're anti-correlated.
or yeah,
it's also a really hard, generically hard math problem to take, 100,000 different telemetry streams and do all the correlation between them. Because certain things, how much time you look at, certain things become correlated and then become not correlated, right? And then the types of correlations, you have logarithmic, you have inverse correlations, you have superlinear correlations, all of those things are there. And if you give a statistician 2 data sets, they can theorize about how correlated they are. If you get a computer 100,000, it's like, I have no idea.
yeah. There's a number of interesting papers on the field of anomaly autocorrelation, and unfortunately, you read them, and almost all of them, somewhere around paragraph 5, say, and we did this in a real-time data set of 12 metric streams. I'm like, okay, that's great. Now that just means that it's completely useless if you have 1,000 metric streams that you're trying to autocorrelate, and then you add in autocorrelation with time lag, and they're brute forcing it by comparing, 1 minute, 2 minute, 5 minute, 15 minute, and so on, just trying to find a correlation. Yeah, it's frustrating that no one solved this unsolvable problem.
And we can definitely, we should talk more about that stuff in the visualization section today. So, Disk.io, IOStat, summary, I really love the columns. Either version, Linux or this particular version. Yes?
I just, as an observation, I just had one. You're showing this, and he was mentioning like trending. It seems unusual to me that we have these tools like IOStat that are, they're based over a period with a roll-up, but there's no indication of like a first or second order derivative as part of the roll-up. When after you've gotten a certain number of iterations, it seems like you could add into there that like this is the rate of change and this is the rate of change, and then that would point out, like he was saying, something where it's steady state for a while and starts to change. Maybe that rate of change is something expected, maybe it's not. But after so many iterations, it seems like a column that could get stuffed in there and wouldn't be too programmatically difficult for most of these tools that produce columnar data.
Absolutely. Having a first or second order derivatives would be really, really cool. And is there an example of an OS tool that spits one out? I don't think.
MRTG.
That's almost everything on that's
MRTG.
first order derivative already. Except for,
Sorry,
except for percent is 8%. Even those are calculated about first
Well,
order.
the error column over here are counters. Those are rates, but
Right.
the second order derivative would be useful on the rate picker.
If you're increasing your error rate, you've already got a big problem.
Right. I don't deny that understanding acceleration and jerk are really useful. I wonder whether or not that's feasible to do in a text-based tool. At some point, you have information overload.
Well, you set colors, do the D-step model.
MRTG shows standard deviation of latency at each hop, and that is, it's not about because the variance, for at least for the purposes of network links, the variance in latency at each hop is a very meaningful metric. And I don't know anyone who still uses traceroute if they have MRTG available, because they produce the same output in effect. The same data is underlying it in effect, but the presentation is such that it becomes immediately obvious, oh, right there, 4 hops out is where something's noisy, something's flaky.
That's all of MTR.
I say MRTG, I'm sorry. I've been working on my slides late into the night, and MRTG is right in the middle of it. MTR is what I mean, MTR. Don't use MRTG.
Interesting problem with MTR.
Yes.
You hit Control-C, it wipes everything. Where was the information?
Yeah.
So that's a great example where a good tool would be great.
Yeah, I kick myself every time I do that. So I have to hit Control S and then copy and paste it, and then, because,
Or you're just running screen and do a hard copy.
yeah.
Yeah, right. So just as an example of trending, so adding a column to IOStat so you can see how things are trending. Well,
Well, it'd be a row.
this is something that we commonly use for trending, right? So the 1, 5, and 15-minute load averages. And so mentally I consume these often, briefly. They're not very useful, but they're a little bit useful.
Have you ever, you ever had a really intelligent question resolved from looking at those numbers? On Linux particularly?
On Linux, since they added the disk I/O by uninterruptible wait, I pretty much don't use them.
Right.
But yes, I have had useful results where the customer says, I have a CPU issue, load average 0.0, okay, then I'm immediately looking at disk. I mean, I look at this for 10 seconds, that's it. Also, because it's got the 1, 5, and 15 minute load averages, if this was 30, 15, and 10, actually, the one I do see all the time is when I'm getting a performance ticket escalated, and they say, Brennan, you need to log into this system and look at it right now, and I see load average 5, 15, and 40. And it's like, well, I think I missed it. Like, did this happen 15 minutes ago? Because the problem isn't happening now. And so it gives me the idea of how things are trending overall. Now, on most systems, except for Linux, this is CPU only. I would like to see it separated for disks, memory load, network load. So I would propose something like that to give you an idea of trends for what's happening to disks. So if I get that performance escalation saying, customer had a really bad disk issue, go look at it, and I can say, well, it looked like I missed the boat. It happened a while ago, but things have gone back, things have settled. Or I can look at it and say, oh, it's getting worse. It's like, used to be bad, now it's really bad, it's super bad.
Where I see something like top is, because it's almost the first thing I do whenever I'm looking into a system, I'll just run top, because it's the very root of your diagnostic tree, in that top alone could cut out half of what you're looking for. You know, depending on which way, is it flat, is it going up, is it going down? It basically allows you to eliminate large categories of possible issues.
Right, it can take issues off the table and it can direct analysis.
Another one along that line is ATOP. Now, I'll split out the disk statistics to show you each disk and what its I/O load is. It'll show you all the individual CPUs and what they're doing, which you can sort of get a feel for from regular top, but it's a little bit easier in ATOP. Plus, I think it gives you network statistics and some other stuff as well.
Yeah, ATOP's good because it also does proc event tracing. And so if you have short-lived processes, like you're doing a software build, top will miss it in the samples, but ATOP will see it. I mean, I get a lot of that as well. So anyway, this stuff, love it. Metrics, if it's trending, I would like to see this sort of thing implemented. Or something similar, you make this. I mean, the load averages come from either CTSS or 10x. They've been around for decades. We may be able to come up with a better set of metrics. Maybe that's something you might think about today. But something to show overall trend for usage patterns. Now, when John said we want to look at things like temperature, that to me sounds like jumping to the answer for a problem. And that's fine, it works for you, it works for me in my environment, I solve a bunch of problems with it. What I want to talk about, just briefly before we move to the next topic, is instead of jumping to the answers, going to the question and then picking that apart. And so using a methodology to get to the problem. And this is what, just very quick rundown, this is how I currently debug disk issues. Customer says I have a disk issue. Okay. We added metrics to the kernel that does the following. These are counters that get tripped if you have an I/O greater than 100 milliseconds, 10 milliseconds, 1 second, 10 seconds. These are done per tenant. This is a cloud platform, so there's multiple guests. And so for each guest, I can then look at these trip counters. These are measured at the VFS level. And that was also something John said about how there can be a big difference between VFS and what the disks are really doing. Now, VFS, if this is new, I do have a picture of it. If VFS is, this is not a great picture, but I mean, fine. Block device interface, by the way, it's in all Unixes. It's been there since the original AT&T Unix. Block device interface is what manages the disks. VFS was added by Sun in the 80s so that multiple file systems could coexist, NFS and UFS at the time. Now, every operating system does it. As a process, I talk to VFS. And so if I have a disk I/O issue, unless I am doing some raw path, some special raw path, it's usually through the VFS interface. That's where I experience it. Then, a whole heap of magic happens in between with ZFS or EXT, 2 or ext4, whatever it is. And then you have the block device interface and disks. Since that's where the process is suffering the latency, that's where we added the trip counters. Because if the customer says they've got very slow disk I/O, which is 100 milliseconds or 1 second, and these counters are all 0, they have not had disk issue, they've not had a ZFS issue, they've not had anything below stack. And we can immediately direct the investigation into other areas. So, one thing we do, look at those trip counters, we add them there for a reason. I'd like to add them at other layers of the stack as well, so that we can narrow down, if latency has appeared at the disks, or didn't appear at the disks, where did it appear?
What command did you run to get that? That's a Solaris box, right?
Yeah, this is an Lumos system. These are only added to a Lumos. But like really, these sort of things, the hard part about these counters is not the software, it's just the idea. It's like, this is a useful count.
Is there an equivalent of the Linux for that, or?
No. Right now on Linux, you'd have to roll dynamic tracing, and then you've got a bit of a problem because none of the dynamic tracing ports are production safe yet. But
Or laptop safe.
or you fix it.
Will systems have anything like that in this, or is it a lot more crude?
No, SystemTap does the same thing as dtrace. Unfortunately, I have a panic and freeze as well, but it's SystemTap and dtrace. SystemTap was designed to have the same feature set as dtrace. In fact, it's extended in a few areas. So I use SystemTap a lot as well when I need to. I'll use whatever tool it takes to solve the problem. I think that's something Theo has championed before. So IOStat, great. Trip counters like this is great. Other things include going down the stack and trying to see where the latency originates. So if I confirm that it is at the VFS level, and I can also use dynamic tracing scripts to measure it, I can then step inside ZFS or whatever the file system is. Do I have a picture of ZFS? Do I have more details of this? This is just an old presentation I gave on ZFS performance. It's the idea is that I confirm that there is a problem, and then you work down until you get to that cause. There are a lot of problems with disk I/O that are not caused by the disks. And they're caused by the file system or the kernel or various other factors. I debugged one of these recently where the customer were complaining of 10-second disk I/O. And it's like, 10-second disk I/O, that really, really sucks. We looked at the trip counters and they hit it. 10 second at VFS. Now what? We want to perform drill down analysis. If we've got 10 seconds at VFS, did we have 10 seconds at ZFS and at the block device interface? We don't have those counters yet, so I had to do this manually. And so rolling dynamic tracing scripts at each of these levels. At the block device interface, I use tools like IOSnoop, which I'm still running on my laptop. Absolutely no events of 10 milliseconds. So at that point, we knew that we had 10 millisecond latency up here and not down here. This is like 10 milliseconds or less. And so it drew attention to look in the middle and what was happening within the kernel. And using dynamic tracing, you can do things like, if I block, what thread called me to do the wake up? So if I block on a conditional variable, what thread is ultimately doing the wake up, which could be something you completely didn't expect. This type of analysis showed out it was something completely unexpected. The system was running ZFS. ZFS has an adaptive replacement cache. It periodically cleans up its size. And this was a 256 gigabyte system with about a 200 gigabyte ZFS arc. And when it cleaned up its size, it was dropping by, 10 gigabytes at a go. And that's too much, because it would hold various kernel mutex locks and then dump all these buffers from memory. And whilst it's holding those mutex locks, I/O can block behind it. And so this is why the customer ended up experiencing what looked like 10-second disk I/O, but the problem was entirely software. Nothing to do with the disks. The problem was entirely coming out of CFS. So that's an example of using a drill-down approach to go from a problem down to the cause. In terms of the actual metrics we like, so I do like those sort of things, but I do like IOStat. It's not just at the disk I/O level. We want to see that at other levels, which is... So here's a very similar looking tool that we added to Lumos called VFSstat. And if the columns look like IOStat, there's a reason for that. It's modeled off IOStat. VFSstat is IOStat at the VFS level. And so you can run VFSstat for VFS and IOStat for the block device interface, and then you can correlate to try and understand the difference. And as I helped, this is written by Bill Piefsky, but he consulted with me on how do I design these metrics, which is kind of why we're here. And I said, IOStat is great. I want to see workload applied and the resulting performance. This actually includes columns for disk throttles. So that's actually one thing that you do want to include in any tools. Old-fashioned tools like IOStat, even though on this version I can add a counter column, which is pretty cool, where's the column for any resource controls? We're in cloud computing these days. People often apply resource controls to, or C groups or whatever it is, to control or throttle per tenant behavior. If I am a tenant and I'm trying to monopolize a resource, what am I going to hit first? The resource control or the physical device limit? Depends how it's configured, but it's often the resource control. So you kind of want to see that first. So if we redid IOStat today and MPstat and VMstat and all of these tools, would we actually have a column showing the resource control limits and then the physical limits because you're a guest? And you need to understand the limit you'll actually hit before the physical limit. So it entirely depends on the guest type and architecture. But food for thought. VFSstat is at least an example of where we have gone and done that. We have actually added the resource control statistics so that Bill can see that they've hit it. I wanted to, just as part of summarizing disk I/O, this is on my blog, but I summarized it more neatly in my book on systems performance, so I think it's a bit easy just to summarize the topic from these pages. And this is the difference between logical I/O and physical I/O. Now, this is just an important topic I wanted to very briefly present when we're talking about disk I/O bottlenecks, and that is how what the application sees is what it sends to VFS, and what the disks do can be completely different. And I've broken this up into 4 reasons. There's unrelated reasons why the disks will be busy, idle, whatever, when compared to the application. So disks may be busy because other applications are using them. I get this all the time. Customer says, my application's performing bad. I ran IOStat. IOStat looked bad. Therefore, connect the dots. And you say, well, IOStat's showing another tenant. It's not you. So it could be other tenants. There can be other kernel tasks as well. So in CFS can do disk resilvering. And it can also do scrubbing for checksums. And there's no process doing this. So suddenly my disks are starting to do work. It's a very low priority work. But if you're trying to you're looking at your application, you're a developer, and I'm setting my application cache sizes so that I'm caching and not using the disks. And you're pulling your hair out because you're saying, but the disks are active. I thought I'm caching it. It's because it's unrelated. That disk activity is coming in. It's actually originating from the file system. No process is asking for it. That's unrelated. They can be indirect. So file systems generally do either prefetch or read ahead, where I will request a few blocks at the VFS level. Now at the block device interface, it will request more blocks in the future so that it can pre-warm the cache. Again, this is confusing because if at my application, I'm only doing 100 IOPS, but the file system has detected it as prefetch, and the disks are doing 1,000 IOPS. Because it's kind of random, and it doesn't end up reading the full streams or whatever. There's a level of interaction here. You can see I/O that is deflated. That is where the I/O at the application level, when you compare it down to the disks, the disk I/O is smaller than what you see at the application. The most obvious one is Filesystem Caching. So my application is doing a lot of reads, but the disks are idle. It's because it's coming out of the kernel, one of the kernel file system caches. File system write cancellation. File systems typically by default will not write synchronously to disk. They will buffer writes for a period of time. And so if you overwrite the same block twice before it has flushed it to disk, it will cancel the earlier write because it just doesn't need to. And so that's where you can have multiple writes at the application level, but at disk there are fewer. So that will cause an IOPS delta. Compression. Modern file systems can do compression. ZFS can do compression. So the IOPS and the throughput you see at the application gets smaller. Coalescing. Linux has the I/O scheduler for this, which is great at merging reads and writes. The ZFS also has VDEVs can do something similar. In-memory file systems, you may be using file systems that just don't write to disk at all. All of those reasons can mean that the resulting disk I/O is quite a lot smaller than the application. So 128 kilobytes. My application is only doing 10 byte I/O or 1 byte I/O, but because of the file system, it has to turn that into a 128 kilobyte read or write. This can create 6 orders of magnitude differences. This can be really confusing for customers. It's like, I don't get it. I'm just doing a little bit of reads and writes randomly, but down at the disk level, it's doing a massive amount of work. Because we like to tune that. And then volume manager parity, which is read, modify, write cycles, also adding additional I/O. So those are all the reasons that as a metric, what you see at the block device interface is actually pretty hard to understand because it may not correlate with the application at all. And some of the proposed solutions would be adding another layer of metrics at the VFS level so that you can actually understand what's happening at VFS and then compare that with what's happening down at the disks.